Good evening, everyone. My name is Andrew. I'm one of the technology officers at the University of Toronto Design League. Can you guys hear me all right?
Yep, all clear.
Okay, perfect. So thank you for coming. And today we'll be doing our annual 3D printing workshop. So here is our agenda for the night. So first, I want to talk about some of the history and applications of 3D printing. I want to introduce you to different types of 3D printing technologies. I also want to talk about a little bit how you can design CAD for specifically 3D printing, how you can process a CAD design and optimize it for 3D printing, how you can operate a 3D printer, what are some of the common problems that you see in 3D printers today, and how you can fix these, how you can improve a print quality by doing some post-processing techniques, as well as several safety precautions. So just before I get started, I want to talk a little bit about my own experience with 3D printing. So I was introduced to CAD at a young age. I was really interested in 3D printing in high school. So I actually used a few of those in my school's makerspace. And so by no means am I an expert in 3D printing. I'm just really passionate. And I want to share some of the knowledge and experience I have had with you guys. So before we get started, I also want to show you a video of 3D printing time lapse. So this, yeah, perfect. So this is hosted by Prusa, one of the largest consumer 3D printing manufacturers in the US. And what they do is they take print videos from their customers and they do a collage of some of the best prints per week and they share it on their social media channels for promotion. So this is one of their weekly prints and it showcases what their machines are capable of. I think this is a good video introduction to some of the things we're going to be talking about today. So yeah, enjoy. So yeah, cool. I don't know if you guys watched Top Gun, but it's pretty nice. And this is just one of the things that 3D printers are capable of today.
Just quickly, Andrew, I'm just going
Yes.
to introduce myself quickly. So I'm Kyle Damra. I'm the technology director here at UTDL. We're accompanied by technology director Andrew, who is directing this workshop, as well as Shahir, who's hosted workshops in the past. And we also another technology executive, Yash, who's unable to make it just due to time zone issues right now. But we're all about our club is for innovation and design, going from the digital workspace into the physical workspace, if that be through CAD and different simulation and modeling programs, which we've done in the past. And today's our 3D printing workshop, as Andrew has mentioned and showed us the initial video here. And we have a couple more workshops on Arduino and Fusion 360 occurring in the next coming weeks. This is all in preparation for real world events, school projects, if you want to tinker and just want to start building yourself, and also for in preparation of our design-a-thon, which we're still being hosting. It's going to be online nearing the beginning weeks of February. More information on that will be provided and can be found on our website. Today's workshop will also be recorded and posted on our YouTube channel. If you're to search on YouTube, utdl.tech, we are the first one that comes up, and will also be made available on our website. Thank you very much. And Andrew, back to you.
Yeah, perfect. Thank you very much, Kyle. Just before I keep going, can you guys see the participants list on my screen? And is that blocking content?
Nope. Right now, currently, all we see is the introduction, history, and application slide. There
Okay.
is no links or any windows on top of
Perfect. Thank you for that. And if we may continue, I want to talk about some of the history and applications for 3D printing. So, when you see a new technology, when you see emerging technology, you always want to understand how it starts, right? So for 3D printing, it actually was invented around 40 years ago. So it's not a new technology. So in the mid 1980s, a gentleman named Charles Hull was able to create a 3D printer. So the guy was like, okay, so injection molding is too expensive. Laser cutting doesn't have the geometric capabilities that we need for prototyping. I'm going to make something new. So on the image on the left, you can see a very large scale industrial 3D printer from the 1980s. And yeah, so basically, the printer you see uses a very specific technology, uses a laser, right, to print. And we'll come back to this later. There are a large variety of different 3D printing technologies. And the first one that was created used a laser and a liquid material that was very sensitive to that laser. So it basically hardens when the laser draws on it. And fast forward 40 years, there's a lot of applications for 3D printing, right? You might have seen 3D printed chemistry models in the classroom, or biology models for dissection. You might have seen maker spaces in different high schools, universities. We have a maker space at the University of Toronto, and they have quite a few 3D printers in their 3D use. You also see applications in more generally engineering prototyping. So, as I mentioned, injection molding is more expensive, is sometimes time consuming. Things like subtractive manufacturing, like CNC machining and laser cutting, has its geometric limitations. So, for instance, if you want to prototype a product and you want to tweak it on a very continuous basis to fit the application, it's very difficult. It's very expensive and time consuming for you to, let's say, make injection molds for each of the iterations. Um, what you can do is you can use a 3D printer. You can continuously tweak your designs on the computer. So you can design something, change its design, and you can use a 3D printer or multiple 3D printers like you see on the image on the top right. This is a 3D printer farm. You can use a 3D printer farm to prototype different iterations for the same design, and that will save you a lot of time, right? In the video I just showed you, the print took around 20 hours or so, and that's a very large print. So for prototyping purposes, 3D printers are much faster. Some of the 3D printers we have today are quite advanced. You can use them for aerospace applications. So on the image in the middle to the right, you can see a 3D printed part for a jet engine. And so the some of these applications allow you to use, right, different technologies like 3D designing and apply them directly to industrial applications, right? So aerospace, automotive, things like architecture. You can design architecture models on Rhino in a computer, and you can print them out using different colors, different materials. You can use that for demonstrations. Like if you're a realtor, you can use that for um, telling investors about this new project you're doing. Or if you're an architect, you can use that for physical simulation purposes. If you want to determine the structural integrity for your print or for your actual design, you can print it out and test it out. And then the last application I want to talk about is medical research and medical application. So on the image in the middle, to the bottom, you can see a 3D printed prosthetic hand, right? So we know real prosthetic hands are very expensive. It's ranging anywhere from 20 to 40 to $100,000 depending on the functionality, and not everyone can afford that, right? So if you want to 3D design a 3D printable prosthetic hand, you can then ship that to a developing country where people can't really afford the $30,000 prosthetic hands. And something like this will help them be able to carry out daily tasks. So, for instance, if you put rubber pads on the fingertips of this model specifically, you'll be able to grip things. And another benefit for this particular application is that something like this is completely scalable, right? You can be modeled to fit different individuals' hand sizes, and it offers a variety of functionalities. And I just want to talk more about the different types of 3D printing technologies. So when 3D printers were first invented, right, we had the very large bulky machine that uses a tank of ultraviolet light sensitive liquid that gets solidified by a UV light. Throughout the past few decades, different 3D printing technologies have emerged. There's also different types of 3D printers in terms of the purpose. So there's ones that are used by consumers, like these ones you see in the middle. There's more prosumer machines, and then there's all obviously industrial applications. They're much more expensive. They're sometimes very difficult to operate. You probably require professional technicians to use them. Um, we get more into different types of 3D printers. So the first one I'll talk about is a stereolithography or SLA 3D printer. So this particular machine, right, uses what Charles Hole invented in the 1980s. It has a tank of UV sensitive liquid. We call that liquid resin. Um, at the very bottom of the apparatus, we have what we call a print platform at the very top, and we have a laser, right? A very thin, very fine laser controlled by gyroscopes and fine stepper motors that carry out very precise movements. And so, what this printer does is, at the very beginning, this print bed lowers into the resin tray. It leaves a very, very thin layer of space between the bottom of the resin tray and the top of the build platform, and the laser shines through the transparent resin tray and solidifies some of the resin that's in between. And what that does is that allows you to layer by layer create very thin um, 3D solids that when you move the um, print bed continuously layer by layer upwards, you end up with a 3D printed object. And this particular SOA 3D printer uses bottom up motion, and some SOA 3D printers also have top down. Um, we'll come back to that later. A very similar technology called digital light processing, DLP, uses instead of a laser, it uses a projector, a DLP projector specifically. So these projectors are known to emit ultraviolet radiation from the lens. And instead of having the laser draw a 2D shape, we have the projector project the shape all at once. Right? So a laser is very thin, very fine. It has to draw multiple lines in order to create a large 2D shape. Um, DLP is more efficient in a sense that it creates a 2D shape all at once and is able to solidify the print layer by layer. This printer in particular uses the same bottom-up motion as the last one, right? And you can see here, this is the build platform. This is the resin tray, and you can put resin in here, and this apparatus would just essentially move from the bottom upwards. Now, the top-down 3D printers have, instead of this apparatus, a tank of resin and a platform on the very top with a laser attached to it. And what that does is that when the platform moves downwards, it merges the already printed part into the resin, and the laser on top would be able to solidify a new layer. And the next technology I want to talk about is selective laser sintering, SLS. This is a more industrial application. So what happens in this scenario is you have a tray of powder, right? Usually is nylon. You have a tray of nylon, and what happens is we heat that nylon to a few degrees below its melting temperature, right? So let's say this specific nylon melts at 160 degrees. We would heat that up to 157, 158, just before it starts to melt. And we have a laser, right, that traces out the 2D shapes layer by layer. And when the laser traces out, when the laser focuses on a specific point on on the tray, it actually helps melt the powder and solidifies it, creating a thin 3D object. And when you do that layer by layer, you create a 3D object. So after each layer is printed, there is a mechanism called the recoder that goes around the entire tray to make sure that the next layer, the surface of the next layer is going to be flat and there's no holes or blemishes in the print. And next, here is the most popular type of 3D printer that we use today. It's called Fused Deposition Modeling, or FDM. You might have seen this printer in the My Hall facility. You might have seen the one I showed in the video, the Prusa 3D printer in the makerspace as well. These are very popular. They're the most consumer 3D printers out there. They're also more affordable to purchase, operate, and maintain. So what this 3D printer does is it pushes a very thin strand of plastic we call filament into a very hot, extremely heated mechanism called the hot end and melts that plastic. And when it melts, we deposited it onto a print platform. You can see at the very bottom here. So what happens in this scenario is the print bed would move up to the very bottom, very close to the hot end, right? The plastic will get melted, it gets deposited onto the print bed, and the print bed would move continuously down layer by layer, creating your plastic 3D object. And so what pushes the filament through into the hot end is an extruder. There's two types of extruder configurations. In this situation, you see the extruder is installed somewhere in the back. This is what we call a, so this is the hot end. This is a filament tube. This is extruder in the back. And what the extruder does is it pushes the filament through the extruder tube into the hot end, right? And there's the other configuration you can see in this picture. The extruder directly extrudes the filament and pushes the filament through the hot end, and the hot end would deposit that onto the print bed, right? So um, there's a variety of different configurations you have for different 3D printers. Those are just two of them. On this 3D printer specifically, you can see a few more features that I want to point out. Um, the first one is the print bed, right? So on different 3D printers, sometimes the print bed is removable, sometimes it's not. Sometimes the print bed has a flexible attachment you can take off and you can flex to remove the print, and that makes it much easier. You can also see a cooling fan for the hot end, right? And this is directed to where the hot end is shooting, which means that it's going to cool the plastic down. And we'll talk about the application of that later in terms of being able to print overhangs and bridges, right? Some 3D printers come with a print display, some do not. Most of them do, and sometimes you're able to directly print using the print display. So there's two ways you can control your 3D printer. The first one is if you connect your 3D printer via USB to your computer, where you can directly connect your printer to your printing software. You can install the driver and then you can start sending code to the printer for it to start working. Or you can use an SD card. So what you do in this circumstance is you download the design, you process it, and you copy the file from your computer to the SD card. You move the SD card to the printer and then start printing using the print display. So moving on, I want to talk a little bit about how you can optimize your 3D designs for 3D printing in particular. Right. So on the top image on the right, you see what we call a overhang. And moving from the left to the right, the overhang gets bigger and bigger. And as you can see, when the overhang is larger, the print quality decreases significantly. In fact, on the very right, the print that you have is essentially not usable, right? So you want to avoid large overhangs like these for fused deposition modeling 3D printers, right? What happens here is the filament extruded, the melted filament, the melted plastic does not get cooled fast enough in a sense that it will be able to stay in shape in midair, right? So you can see that there's kind of like a spaghetti formation on the bottom of the overhang, and that's what happens when the plastic doesn't cool fast enough. It essentially drops. Right. On the second picture here, you can see this is what we call bridging. The larger the bridge, the poorer quality the 3D printing. So you want to avoid very long bridges. These not only do not look good aesthetically, right, but also there's the structural integrity is compromised when the model isn't as printed out as you design. Um, in terms of optimizing the use of material, you want to avoid extremely big blocks, chunky blocks of um, design, because you want to save some filament, and it would take a long time for your printer to work through all of that mass and volume, right? So when you we'll do a demonstration on this later, but when you design, you want to make sure that uh, structures are hollow when they can be, and things are taken out when they're not necessary. And the last thing you should keep in mind is plastic properties, right? So there's different types of 3D printers, but in FDM, there's also different types of plastics you can use. So the most popular ones are ABS and PLA. We use PLA in the MyHealth facility. And before you design something, you want to keep in mind the properties of the plastic, right? If you're considering a real world application, you want to see how the plastic can keep up with the daily stress and strains. If you're doing simulations, you want to make sure that the properties match or is scalable to what the real world application is later. And next, I want to talk about digital file processing, right? So it's very important that you understand how we get a 3D design to the 3D printer. So on the left, you can see a CAD design, right? What you do essentially is you export this CAD design as a .stl file. You put that into what we call a slicing software. So that slicing software will process the CAD design file and turn it into very thin slices, and that would be converted then into a code flavor called .g code, right? And this is what we put into the Arduino board of the 3D printer for it to start following these commands and print. So there's a variety of different slicing softwares, right? If you're a hobbyist, you may use Cura. Um, there's also Slicer for Prusa machines. So there's a Slicer Prusa edition specifically for some of the Prusa 3D printers out there. There's also Repetier Host, a older software that's not as used or popular today. And there's also Simplify 3D. This is a paid software. It has a variety of functions. I personally use this one, but there's also a lot of alternatives available out there. Right. So next, and I'll do the demonstration on this later. When you import a 3D design onto the slicing software, there's a few things you have to do to make sure that it comes out all right. Right. So the first thing is, like we talked before, you want to avoid all the overhangs and bridges that are too big or very chunky blocks. You also want to change the orientation, right? So if you can visualize how 3D printer works, it prints layer by layer, and the print head or the print bed will move vertically. So that means it's going to have more strength in the horizontal direction than the vertical. So if you pull in the horizontal direction, it's going to have more strength than if you pull in the vertical direction because of the layer separation there. So depending on your application, you want to change the orientation of the print so that it matches up with the direction of the stress, right? Um, if you want, you can add supports to the different prints. So for instance, if you have to print a large overhang, but you don't want your printer to mess up, then you have to add supports for supporting the structure to print in midair. There's a variety of print settings for different print qualities, different print speeds. We'll do a demonstration on that later. And after that, you have to send it to a machine for printing. So here is a few additional settings, right, you should keep in mind. Um, So the first one is what determines print quality. We call this layer height. So this is essentially how thin or how thick a printed layer is. The industry standard or average ranges from zero point 0.1 to 0.3 millimeters. Anything smaller than that would take too long to print, and anything larger than that would be a significant decrease in print quality as well as the strength of the print. So we know that it will use a lot of material if we printed the plastic object solid. So something that we have in the software is infill percentage, right? So usually when you print an object, you use 15 to 25% infill, and that help you a lot on maintaining the structure of the print without printing it and wasting too much material if it's solid. Right? Um, but then there's different applications, and again, you have to tweak that for the application you're printing for. And with that, you have to have top and bottom solid layers so you cover up the infill. Right? Let's say you're printing a plastic block, you want 3 to 5 top and bottom solid layers so that the 15 to 25% infill isn't shown on the surface of the print. There's also a variety of different infill styles. There's rectangular. The rectangular one is the fastest. The triangular one, only available in certain softwares, is the strongest. There's also 3D infill styles, like um, show in the next image. So the next setting I want to go over is the hot end temperature, right? So your 3D printer has to heat up to a specific temperature to be able to melt the plastic that you feed through it. And so in the settings, there's the hot end temperature setting that you can utilize to heat up your extruder, your hot end to maybe 180 to 210 degrees for PLA, or 230 to 245 for ABS, and even higher for PETG. The print platform on certain 3D printers can also be heated to around 50 to 60, sometimes to 100 degrees for a variety of different filaments. And the reason that we heat up the print bed is to prevent the print on the bottom from cooling too much and then shrinking, right? So what happens is that when the print is deposited onto the print bed, if the print bed is only 20 degrees, the print is going to shrink very quickly and is going to detach from the bed from that shrinkage, right? It's going to decrease in size and it's going to detach from the bed. By heating the platform up to 50 to 100 degrees, it allows the print to shrink on a slower basis, and that'll make sure that number one, your print stays on the bed, and number two, there is more uniform shrinkage when the print is complete. Right, so here are the different infill styles I was talking about. So grid, rectangular, these are the fastest methods. You can see honeycomb right here is very strong. You can see 3D honeycomb, which is one of the 3D infill styles. It looks nice. It looks awesome, actually. You have concentric. This is more for if you don't want to print any top layers, but if you want your print to showcase some sort of specific aesthetics. Hilbert. Some of these are rarely used in real life applications. They're more for if you want to do demonstrations or like a display for what your 3D printer is capable of. There's also different infill percentages, right? So right now we're using honeycomb, and you can see the difference between 5 and 10, 10 and 20, all the way up to 100. So at 70%, the print is essentially pretty much solid, right? At 100%, you can see it's essentially what a top layer would look like. And if you print your entire object using 100% infill, that would be a waste of material. So as I mentioned before, it's very important for you to orient your print correctly, right? If your tension load is vertical and you're printing the part vertically, the part is going to be very weak, right? On the other hand, if the tension is parallel to the layers, right? So if you print your parts, your layers um, perpendicularly to where the stress is applied, right? So you're printing this way, and the stress is being applied sideways. It's going to be much stronger. Just a few more settings before we go into the demonstration. So plastic at 110 degrees is very viscous, right? It's essentially liquid. So when this extruder draws a shape, it has to stop extruding after it finishes drawing that shape, right? But then when the extruder stops extruding, the plastic may not stop coming out. And we call that oozing, right? And to prevent that, right, we don't want that to be on the inside or the outside of the print. It's not going to look very nice. To prevent that, we have a setting called retraction, right? So what that does is it stops extruding or retracts the filament backwards when it's finishes printing a layer, and that makes sure that the filament doesn't ooze out, right? So the backwards pressure created in the nozzle itself will help keep the plastic inside the nozzle. But then when you retract, right, it's going to draw the filament backwards. And so you have to use the setting called extra restart when the next layer starts printing to make sure that there is no filament gaps in the nozzle itself. So there's also the extrusion multiplier. It determines how much film extruded. So let's say you print an object, right? And then you realize, oh crap, there's not enough plastic in the print. It's looking like a spider web, right? What you can do in this case is to increase the extrusion multiplier so that the print is more solid or is up to the standard that you like. There's also the cooling fan. So on most 3D printers, there's two cooling fans, right? One of them is for the hot end. So the hot end gets heat up to 110 degree, 210 degrees. We don't want that heat to go to the rest of the printing mechanism, right? That may melt some of the other components. So we use a cooling fan to cool off a heatsink at the very end of the hot end, right before the heating mechanism. And the second fan we use can be used to cool the print instantly when it's extruded out. Right, so that will help you with bridging, overhangs, printing supports, and things like that. So here is the fun part of our workshop. I want to do an actual demonstration for in Fusion 360 and Simplify 3D to show you how to operate some of the things we've been talking about, right? So first is 3D printing, the 3D design part optimization. Right? Can you guys still see the screen? Cool.
Yes, we're able to see it.
Awesome. So you can see here we have a few objects here. So first off, one thing that I mentioned is you want to avoid printing very large blocks, right? So this object right here, you can optimize this object by number one, changing the infill percentage, right, to 15-25%, or you can do that by making it hollow, right? So let's say you only want the force size of this object. What you can do is, if that's the application, you can take this whole thing out, right? Um, right, so that will save you some material and sometimes even make your print stronger because you have more solid lines in the middle, right? So this is okay. However, if this is how you orient the print, there will be a problem here, right? You can see there is a large bridge that the 3D printer would have quite a bit of trouble printing, right? It's a very big overhang right here. So what you will have to do in this case is you have to reorient the model to print better, or you have to implement supports. So here is how you can orient the model better, right? So if you want, what you could do is turn this entire thing 45 degrees, right? If you want to turn this over to have it stand on, let's say, 1 point out of the six, or out of the eight, sorry. And so what you have to do is, if you wanted to print here, actually, I'll just um, not an expert on Fusion, but so instead of having this 90 degrees to the print platform, when you turn this 45 degrees, let's say to the right, then the overhang would be only 45 degrees and your printer would be capable of printing that, right? So for a consumer FDM 3D printer, most of the times if you have something that's less than 50, 60 degrees of an overhang, it should be able to print. A safe limit that I set for myself when using 3D printers is 45. And yes, Sohyo?
Yeah, I just wanted to ask, so if we rotated by 45 degrees, wouldn't we also need to have supports on the right face?
Yes, so what would happen here is, man, I wish I can do this. I don't know what's going on. Yeah, hold on.
Mm-hmm.
I'm trying to. Hmm. Okay, let's do this. So, man, that is not what I'm going for. Huh. So if I rotate this by 45 degrees, right? What would happen here is that it would be printing on a very, very thin point, thin line right here, right? So what you have to do is to create some sort of support structure on the bottom that allows you to stabilize this point. So what you could do is, if you want to, yeah, now this is oriented really weirdly. Hold on. So what you could do is essentially create a base for your solid.
Mm-hmm.
And so if you have something like this, right, and you merge the two objects, it actually wouldn't necessarily require supports. What you have is better quality on the size of the print, right? There is no um, structures more than 45 degrees. Actually, this is not really a good example because you require supports here. But in a sense, when you print in a different orientation like this, you require less supports, and the print would come out in terms of to come out better in terms of quality.
Mm-hmm. Mm-hmm. Okay, thank you.
Okay, cool. And the next example I want to do is very large overhangs, right? So this is, let me just extrude here. So this is a pretty large overhang on the bottom of the print, right? And you want to avoid something like this when you use a FDM 3D printer. So what you could do is you could implement supports here. You could reorient the print so that it's not on the downside of the print itself. Um, so for instance, let's say if I rotate this by 180 degrees and this is now facing up, right? The 3D printer would print very nicely, right? The top surface would be very smooth, and this surface itself will be printed very smoothly as well. Um, if I oriented this the way it is, it would come out. Perhaps certain 3D printers will be able to manage that, right? If you have sufficient cooling, but others may come out as very bad layer adhesion or just a bad surface finish in general. Right? Okay. So when you have a CAD design, what you want to do is you want to export this as an STL file, right? So, man, how do I export? I have to save this. Yeah, give me a second. Huh, interesting. Okay, sorry, my bad. You have to export it, right? So after you save it, you have to export. Um, let me just choose where I want to save this as. And you have to export as an STL file right here. This is kind of small though, right? It's hard to see. But yeah, so essentially, after you export, you have to import that again onto a 3D slicing software. And just give that a second there. Huh. So while that exports, I'm going to show you how to orient prints on your 3D printing slicing software and how to add supports and change some of the settings. Well, this is kind of slow though. Anyhow, let's just take this object that here, for example. Right, this is actually a pretty solid example of what I want to talk about. So you can see here, if I remove all supports, right, let's just talk about this model for a second. It's very nicely designed, right? But you can see there's a lot of overhangs at the arms, at the hands, under the glasses, under the hat, and also on top, right? So if you had your 3D printer print this directly, you'll have quite a bit of problems managing some of these um, just printing in thin air components, right? So this model in particular, there's actually not a lot of better ways you can orient it considering how it's designed. So what you would do in this circumstance, you have to implement supports for the model. So this software is called Simplify 3D. There's a customized support generation. So here you can set the maximum overhang angle to whatever your 3D printer will be capable of, right? So this is something that you have to test out. Mine is comfortably printing 45 dB overhang, so I'm going to set that as 45. I can generate automatic supports. Right? As you can see, the automatic supports aren't really great in a sense that there's smaller supports that the printer wouldn't need, right? There's specific parts that are not being supported, like the glasses. So what you could do is you could use the add new support structure feature, and you can add customized support. So let's say I only want to support, the glasses, right? So what you could do is just add customized supports here. You can do the same for the right side. You can add supports to the arm. Right, if you want, you can add some for the hat here. And so let's say my printer is somewhat comfortable with printing around the neck, or this is too small for me to remove the actual supports. What I can do is just leave this, right? So I want to support the overhang here. I'm going to leave the neck. I'm going to do some supports here, right? Or you don't have to if this part of the print is not really important to you. Right, so this right here will be a bit better than before, right? So if I just did automatic supports, it doesn't support some of the other components I want and has extra supports around places I don't really need them. Right, so that's that on supports. Oh man, my demo is still generating. Is there a way to calculate the strength of these supports? Does it matter? How do I determine the fill density of these supports? Right. So in terms of calculating the strength, the software doesn't actually allow you to do that, but you could determine the infill density for the supports, just like you would have infill density for the 3D print. So I'm going to show you in a second. Right. So here you can see quite a few settings. I'm going to show events. So the first one is it lets you pick the material you want to print it, right? So the material is configured with a specific printing temperature. There's a quality configuration. You have fast, medium, high. So high, it will be a lower 3D printing layer height, and then the medium would be in the middle, and fast would be like a draft 0.3 millimeter layer height. Right? So here's the infill percentage, right? You can change the infill percentage from 0 to 100 to whatever you like. And you can have support infill percentage, right? So support infill percentage can also be changed. they suggest 30%, which I think is actually a fairly good configuration, right? Some of the supports can be quite thin. You don't want them to print uh, in a hollow sense, like you don't want 5% infill for the supports and have them fall over midair, right? Mid print. So you can increase that if you need, or decrease it if you're printing very large support structures. And yeah, so here's some of the other things I've been talking about, right? So the nozzle diameter is whatever your hot end is from the manufacturer. So that's set. Extrusion multiplier is what you can tweak to make sure that your printer is extruding sufficient material. So I can change that to 1.2 if I want to make my printer print, at 1.2, 120% the material it extrudes originally. Um, Here's the retraction settings I was talking about. So here's the retraction distance, right? You can retract for 1 millimeter, you can retract for 10, depending on the printer. So the two FDM printers I showed, the first one, right, had the extruder in the back, right? And it uses a tube, filament tube, to push the filament through. What happens there is that there is a tolerance, right, for the tube that the extruder has to compensate for. So the retracting distance for that printer will be larger than what you have for the second one, where the extruder is directly above the hot end. Right. This is the actual restart distance, right? So let's say um, I retract 10 millimeters, right? The printer would obviously compensate for that the next time it starts printing, but maybe that's not enough, right? So if you realize that there's a discontinuity in the print of the layer, then you can set the extra restart distance to 1 millimeter. It's going to extrude 1 millimeter of additional material, and that'll make sure that the print is continuous. Some of the other settings, not going to go over. They're more for if you want to tweak a setting very specific to a 3D printer. So here's the layer settings, right? So I was talking about how you can have very precise prints for if you use 0.1 millimeters per layer. A medium configuration is 0.2. If you want a faster print with a lower configuration, you can go up to 0.3. You can adjust the top and bottom solid layers to your liking. If you want more solid layers on those two surfaces of the print, you can do that. And then here's the setting that I didn't talk about, the outline perimeter shells, right? So this is how many times you want your printer to go around the surface of the object on the, not the top and bottom, but on the horizontal sides, right? To make sure that the sides are solid, right? You can change that to how many ever you want. I usually use 3. That'll make sure that the printer doesn't waste too much time doing that, but also have a fairly solid outline. Right, there's a lot of first layer settings, right? And what that does is it makes sure that your 3D print gets stuck to the bottom of the print bed. So sometimes you can adjust the speed to be slower than what the other layers are. And that'll make sure there's more time for the material to get stuck to the print bed, or you can adjust the layer and the height and the width. So skipping this and go to infill. So if you have a multi-extruder 3D printer, right, you can use different extruders to print the infill. So let's say you're using nylon to print the very outer layer, but you want a cheaper infill, right? You can use PLA or ABS, right? There's different patterns you can use. So there's rectangular, the grid, triangular, honeycomb, some of the other ones we were talking about. Um, you can change your infill percentages. You can change your infill extrusion width, right? So if you want your infill to print at a larger width so that it's stronger, you can change that. And there's support. So you can also pick your extruder for printing supports. So for instance, there's a PVA material that melts in the water, and you can use that for if you want to print water soluble supports that you can just put in the water and have it melt. Yeah, for sure. And then so some of the things here, are peripheral settings that you could use to make your supports better, right? So there's a support base layer. You can use that to print a solid base layer at the very bottom, or multiple solid base layers at the bottom, to make sure that not only your print is stuck to the printer, but also the supports. So at the very top of the supports, we have something called dense support, right? And so what that does is it creates a smoother surface for the actual print itself to sit on, right? So let's say you have the overhang here, right? But your infill percentage for the support is only 30%. So there's not really a solid layer here for your glasses to sit on. Right? What you want to do is you can have, one, two, or three almost solid dense support layers right before the actual print is going to be deposited. And that'll make sure that the bottom layer for the print is very smooth. Right? Here's some, if you use the auto supports, generate support automatically feature, here's some the settings you can change. And one of the important things about supports is that you have to have a certain degree of separation, right, from the support itself to the print, or else the support is going to be fused to your print, right? So changing this based on the printer that you have will help with being able to remove the supports very easily afterwards. Here's some more settings for the extruder. So I can change this to whatever I like depending on the material that I'm printing. Right. So ABS has a different profile, right? I can change that to whatever. If you have multi extrusion 3D printers, you can also choose which heater it is that you're heating the extruder with. So if your 3D printer has a heated bed, you can change the settings for the heated bed here as well. You can change it to, let's say I'm printing ABS, so I'm going to use 90 degrees. And it really depends on the printer itself as well. So sometimes there may be a discrepancy between what the thermometer is going to tell you than the actual temperature. That's something that you can identify through just testing out the machine by printing a sample and see how well it turns out. So next I want to go over the fan speed, right? So the fan for the hot end is always going to be on. It's on when you turn on the printer, right? But the fan for cooling the print has to be set using software. So the first layer usually doesn't require cooling, right? And the reason for that is we want to make sure the print, first of all, doesn't shrink too much when it gets cooled, and second of all, a huge bit better. But starting second layer or whatever layer you like, actually, you can turn on the fan to from 0 to 100%. That'll make sure that when you print an overhang or when you print a bridge, the print is cooled. And depending on how strong your fan is, sometimes you wouldn't require supports. Right, so here's some um, G-code settings, script settings. So what this software offers you is you can do specific things before you start a print and after you end a print, um, if you want to customize that experience, right? So for instance, at the very beginning, a very common command to use is G28 that homes these 3D printer, right? So you have the different axes for the 3D printer that you want to start from 000 at the very beginning. Right. At the very end, it turns off the extruder, turns off the bed, and disables all the motors. Right. So what that does is it stops the heating from continuing. That saves you power. That actually prevents the burning of material, um, and it also helps protect your 3D printer mechanisms from overexertion. And here's some speed settings. Right. So depending on how fast you want your printer to go and how high the quality you want, you can change the speed, right? So 3600 millimeters per minute for the printing speed is a fairly standard default, right? you can also change your movement speed. So this is what happens when the printer is not printing. It has to move from point to point, right? You can change that. You can also change the z-axis movement speed. So the z-axis really moves slower because it's either moving the print bed, the entire print bed assembly up and down, or it's moving the hot end up and down, right? So it's going to be requiring a bit more time, and it requires more power as well to move. And this software also has a certain bridging settings, right? So when you do a bridge, it lets you define how large the bridge can be before it implements supports. It lets you customize the speed for printing the bridge itself. Sometimes going faster actually helps you print the bridge better, just because the hot end actually pulls the filament, um, so that it doesn't drop as quickly. Or you can also customize the infill for the bridge, right? So when you do a bridge, you want to have solid infill at the bottom because it's considered a surface. But you can also customize the angle for the infill of the bridge to make sure that, if you only print horizontal lines between 2 points, it's going to um, come out better in terms of quality than if you print, the outline horizontally, um, and the infill in a different direction. Okay, so let's do a slice demonstration for this print. So what we have here is different processes that you can create, modify, and add, right? So the one that we just had is called process one, right? And what that allows you to do is to create different processes for different printers you want to use, or the same printer but different settings, right? And so I'm going to add some supports here. Generate expression. No, let's not do that. I'm going to add customized supports like I did a minute ago. All right, okay, I'll just leave it like that. And so what you have here is you have the prepare to print button, right? And what that does is it prepares a visualization of what the print will come out looking like. So you can see here, we did support infill density 30%. We did dense support infill density 70%. So it's almost solid, right? And we did customized support. So there's no supports anywhere else. You can also see we did a support separation layer of 1, I think. So there is a space between the actual print and the top layer of the dense support. That'll make sure it's very easy to remove, right? And so what you can do here at the slider on the bottom is to actually visually see what your print is going to look like. Right, so you can see the infill percentage, it's not solid, right? That's going to save a lot of time for you. And you can see how the printer is going to print out the entire object, right? So the infill that we had here is 35%. And if it looks too high to you, you can change that. Right. Let's say, let's say you do 15%, right? This is going to save you twice the time printing infill than when you were doing 30, 35%, right? A very nice feature of the software is it tells you how long it's going to take, right? It's not a specific, a very accurate time, but based on the printing speed that you have, it's going to tell you an estimate for how long the print is going to take. It also tell you how many grams of filament you're going to use, right? So you're using what, like 11 meters filament, 33 grams, and it's going to cost $1.55, $1.54. So that's all right. Perfect. So now that we have our 3D print ready, right? What you have to do is, actually before that, here's the last thing I want to talk about in this software. You can bring printing over USB, which is when you tether your 3D printer to your computer, you can directly connect it to the printer itself. And what it will have is a control menu, right? When you press connect, it's going to let you configure some of the 3D printer functions, or you can save this to a USB drive. So it's going to save as G code, right? And you can save it as G code as well. And what that allows you to do is to move that to then an SD card, put that in the printer, and then start printing directly from the printer itself. Right. So now let's talk about how you can actually use the 3D printer itself, right? We know how to optimize the design for 3D printing. We know how to put it into a software and slice it, prepare it for 3D printing, put in different settings like infill settings, support settings. Now here's some physical procedures that you want to carry out before you actually use a 3D printer. Right? So chat, great to see you, Khan, and hope to see you in one of our next workshops. So in terms of machine operation, you want to clean and prepare the print platform. So how I do that is I use isopropyl alcohol to clean out the print platform. I preheat the machine. So sometimes it takes a long time for the printer to heat up, right? 210 degrees, 235 degrees is a high temperature. So what you want to do is before you prepare the print, perhaps you want to actually preheat the machine up to the desired temperature so that when your print is ready, you can start printing immediately. So after that, you want to put in your SD card. You want to use the on-screen controls to start the print, or you can use your computer controls to be tethered to the printer, and you can you want to remove some of the debris on the bed, right? So when you clean it, if there's like plastic left over on the bed, you want to be able to clear that. And of course, if everything goes well, your print is going to come out perfect. You can remove it from the print using a spatula. You can take the flexible print bed off and remove the print. But then there's going to be different issues, right? So Simplify 3D actually offers a very comprehensive guide to troubleshooting. So I won't go as in depth today, but here's some common issues, right? So we're going to go over this image by image. If you see the first one, there is not a lot of plastic coming out of the extruder on the first layer. And what that means is that your print hot end is set too close to the print bed. And what you do is you adjust the limit switch for the z-axis manually until the plastic starts coming out so that the first layer is printed successfully. Right. On the second image here, you can see this is the opposite to the first, where the hot end is actually too far away from the print bed. It's not sticking to the print bed. And what you want to do in this is to adjust the z-axis limit switch backwards. So under extrusion is one of the common problems we have with FDM 3D printers. You can change the extrusion multiplier, right? This is when you adjust the settings from 0.9 to 1.2 or 1.3 to compensate for the under extrusion. Same thing applies for over extrusion. The next, I guess, challenge you can experience is if you have gaps in the top layers, that means your infill isn't solid enough. And what you can do is there's remember the remember the settings we had for the top layers. You can increase the extrusion multiplier specifically for the top layers, or you can increase the number of top layers so that the top few layers look more solid. An issue you can have is you can have oozing or stringing. This is due to the uh, extra, extra restart distance and the what is it? Yeah, yeah. This problem is based on not being able to, wait, let me see where my settings go. So when the printhead moves around, right, it's going to create, right, if you don't retract sufficient material, it's going to have stringing around, let's say, the different parts of print where the extruder is moving around. And so when you have that problem, right, you want to tweak in your retraction distance settings and your actual restart distance settings to make sure that it doesn't come out fuzzy. But this is also easy to remove, right? If you have like some sort of a sharp object, you can just take that off. Another issue you may have is overheating. So for the top few layers, you can see that the print is completely disfigured, right? And what happens here is that there's insufficient time for the machine to cool when it prints very small parts of an object and it's focused on printing that small part. It doesn't move to different parts of the print bed to print other objects. This is the only point it's concentrating on. And then there's too much heat for the printed material, right? It doesn't cool down sufficiently. The print head is going to drag the tip of the print around. What you want to do is either increase the heating or decrease the printing speed for the top layer so that allows it more time to cool. And then another common problem is layer shifting, right? You see that a lot with DIY 3D printers or consumer 3D printers. What happens here is it's either there's a blemish in the print that's causing the printer to not move around properly, or there is something wrong with the drivers on the board, control board of the 3D printer. And what you can do in this sense is to essentially add a fan to cool down the drivers more when they're overheating, so it doesn't happen. So here's a few more important troubleshooting tips. So if you have layer separation, that means that the layers on the bottom are not bonding well to the top layers, and that could be caused by too much cooling. So you might want to modify your fan settings to not have the fan speed as high as it is right now. So the extruder has a gear that grips onto the filament that sends it into the hot end, right? Sometimes that could be too tight, and that would result in grinding a filament. And so what happens is your extruder gear would essentially lose the grip after it grinds through a part of the filament, and that results in the print stop printing. You want to do that by adjusting the tension that you have on the extruder. If your extruder is clogged, that could be a gem based on like an alien particle in the extruder. You can, I guess, replace the extruder at the hot end in that sense. And then there could be also insufficient heating due to your print settings. Right? So if you're printing ABS at 200 degrees, when you're supposed to be printing at 235, it's going to clog the extruder because the material is not melting enough. So you can change the settings in the printer as well to compensate for that. So if your 3D printer stops extruding mid-print, it could be, number one, you ran out of filament. So in that case, you had to restart the print with a new roll of filament. Or it could be the extruder is clogged, in which you have to troubleshoot using the clog extruder techniques. Sometimes your infill is not solid. So most of the times you wouldn't actually be able to see this. It's only when a print fails or when you check on the print mid-print and you realize the infill is very weak, then you can increase the infill extrusion multiplier. If you see blemishes on the surface of the print, that's caused by oozing, right? So when your printer restarts a layer, right, it moves the extruder from the bottom layer to the next layer up. And what happens here is that when you don't have sufficient retraction or sufficient extra restart, then it's going to extrude additional material onto the outside of the layer that you don't want. So make sure you change the settings for that. There's one setting in the printer that can avoid gaps between the infill and the outline. It's the overlap setting between the infill and the outline, and that allows you to make sure that the outline, the surface, is bonded to the top and bottom layers of the print. Curling in rough corners, that's caused by insufficient cooling or too much material being extruded. So those are the two settings you want to tweak. Here's a few more. So thin walls is very tricky, right? So these two, when you have a especially small object, sometimes when your extruder, when your hot end size is large, it's not going to be able to recognize or print some of these features. So you have to tweak the settings in the software to say, okay, so I want the printer to print thin walls below 0.2 millimeters, despite the fact that my hot end size is 0.3 millimeters. And the printer will do that when you change the settings for it. You could experience problems with your filament or your extruder that results in inconsistent material being extruded out, right? So the first thing you want to do is to measure the diameter for your filament to see if it's identical to what you have set in the software. Some manufacturers may have tolerances that leads to some sort of issue like this. Um, for warping, this mainly happens with ABS filaments. So what happens here is it's the material being printed on the bottom is shrinking too quickly. It's detaching from the print bed, and it's messing with the rest of the print. And what we're going to do here is to heat the print bed up to a to a higher temperature. And you also want to perhaps apply some sort of a heat set, right? For ABS, maybe it's good to apply like an acetone solution or apply some sort of hairspray or glue that will make sure the print stays on the print bed. We kind of talk about support settings. If you want a smoother bottom layer, make sure you have number one, enough solid layers on top of the support, called the dense support layers, to um, um, actually have a smooth surface for the print to go on. Or you can increase the area that you're supporting, right? If you're only supporting a very small area, let's say on the bottom of this print, if you're only supporting like the 1 point on the bottom of the print, then that may not be sufficient for the surface to be smooth. And the last two I want to talk about is dimensional accuracy and pore bridging. So in terms of dimensional accuracy, your printer never really, it isn't always going to be perfect, right? So what happens is based on the mechanical configuration, the firmware is set so that the machine knows turning the stepper motors by a certain number of degrees, it results in a movement of the machine by this many millimeters, right? And sometimes you have to go into the firmware settings to actually tweak that, or sometimes you can compensate for that when there are dimensional accuracy errors in the software itself, right? So you can scale the object to a different scale to compensate for, if your print is smaller than it's supposed to be, you can scale it to be larger in this 3D printing software as well. And then in terms of pore bridging, number one, if your bridge is too big, use some supports. And number two, maybe there's insufficient cooling that's resulting in a poor printing quality. Okay. So now that your print is finished, right, you're able to remove it from the print bed. But before you do that, you want to make sure that if your print bed is heated to 100 degrees, you want to make sure it cools down first. You can use different tools to remove prints from the print bed when it's appropriate. So things like spatulas and sometimes I use like a flexible print bed. I can just take off the print by flexing the bed. That's also very convenient. You want to clean up any supports. So when we have the layer separation from the top of the supports to the bottom of the print, when you prime in that setting, it's very easy to remove any supports. One thing you may want to do is to send away the layer lines. So the machine prints layer by layer, right? And it may not always be as smooth as you want it. So if you want better surface quality, you can send away any of these lines. I'll show some pictures in the next slide. You can also use acetone smoothing as a technique for ABS material in particular. You can use a 3D printing pen or a resin filling pen to smooth out any blemishes or holes. You can also paint the print, right? So a lot of artists use a primer. They spray a primer onto the print after, and then they start painting, and that will result in a more smooth finish. Right. So here you can see this is just smooth using sandpaper. This is smooth using acetone vapor treatment. Acetone vapor treatment on this one as well. This one uses sandblasting, right? So this is more industrial treatment where you blast very fine particles of sand onto the print at very high velocity, and that will smooth out the surface of the print for you. You can also use different painting techniques. right? And sometimes you're going to spray a clear coat of paint, actually, like glass coating onto the print after you smooth it to make sure that the surface is protected and it stays smooth over time. And last, when you use your 3D printer, there's a lot of hazards, right? Even with prosumer industrial machines, there's a lot of safety precautions you have to take. So the first thing is that your 3D printer operates at very high temperatures and sometimes at very high speeds, right? So you want to make sure that you stay away from the heated elements like the print platform and the hot end as much as possible. So use tools like tweezers to remove any extra additional materials on the print bed or on the hot end, right? The same thing applies to a cooling fan. It operates at very high speeds. You don't want to stick your finger there. The stepper motors and the stepper drivers could be heated because operating the printer requires a lot of precision, but also a lot of force. So the stepper motors can heat up when there's a lot of tension. So for instance, your extruder motor has to push a lot of material through a very thin, very small hole, right? That may cause them to heat up over time. If you have a 12-hour print at the very end, your extruder may stay hot for quite a few hours. Same thing applies to the board. And when you use spatulas or knives or blades to remove prints, be as careful as you can because those can also be quite sharp. So here's some additional resources I want to share before we end the meeting or end the workshop. So Fusion licenses are free for students. So if you want to get an education license and start CADing, we had done a few tutorials on those. Check them out. And you can also download a free version of the software. Um, the Curious licensing software, which is offered by Ultimaker, is also free. And it offers a lot of the settings that we talked about today in the software itself. And then again, Simplify 3D has their own troubleshooting guide. So if you're looking for more detailed, in-depth solutions to some of the issues that we talked about, you can pay them a visit, and they'll have a lot of experts to guide you through how to resolve some of these challenges. Yeah. And if you guys have any questions, please feel free to ask. And if not, I'll say thank you very much for coming. I enjoyed hosting this workshop, and I hope you guys can take something that you learned today to your own design, 3D printing, and some of your own adventures as well.